Okay, hi everyone. Today we have a double feature today. We have our speaker for the morning is Ilya Volkovich from Boston College, and in the colloquium we have Avi. So speak to me.
Thank you, Rit. Thank you, Avi. So I have to say I'm very excited and almost very to be here again. I was here for 2 years, 14 years ago in this room. I can tell you how much I learned coming to those seminars every Monday, Tuesday. I was here, so it was really an experience, and I want to thank again Avi and Irit for allowing me to come here again. Thank you. Also, I'm going to talk about linear ordering principle, lower bounds for that. That's a joint work with Edward Hirsch. And I mean, what I'd like to do is I don't going to give you a lot of technical details, but rather try to inspire a discussion because there are a lot of things to discuss here. And I remember the discussion that we're going here. I hope the intensity did not come down after 14 years. It only, if anything, become better. So I'm going to talk about that. So please ask questions and now or after the class. And sort of this work is, you can think about a small, maybe a tiny link in the big chain that talks about the questions of what are the relationships with different complexity classes. So this is like a big chain, and hopefully we could make one more link in that, or something that a different way to put it, and something that I've learned by listening to the talks here. And I heard this quote many times while I was here, and this is actually very relevant to those kinds of talks, is there is a gap between what we believe and what we can prove, right? So do you want to guess who said it? Multiple times, and this turns out to be still, when I think about this turns out to be the guidelines, and I'm going to refer to that. So what are we talking about here? So we start at the top. We're talking about the first thing that we want to talk about is total function. So just for some terminology, a total function typically represented by a relation. So you have a relation, and total means that for every x, for every instant, there is a solution. So that's in general what makes a function total. Now, to be more specific, if you also insist that this relation can be verified in polynomial time and the witness is polynomial, then that's a special class of total function bearing the name of TF and P. So TF and P is a very important class. It has many connections to proof complexity, which we're not going to talk about in other areas. But what we're kind of trying to do, we're trying to learn more and more about it. And I mean, there are many natural problems that are in this class, things like integer factorization. So again, the point is there exists a solution. We know it exists, but how do you find it efficiently? So for integer factorization, for example, we know by the fundamental theorem of arithmetics that every integer has a factorization, a unique factorization. How do you find it? So Nash equilibrium. So one observation kind of based on the definition is that TF and P can be contained in FP to the NP. So you can solve it in polynomial time if you have oracle access to NP. So this is, of course, not an exact characterization, but this is a bound. So what we want to do is we want to show or try to learn more problems and show that they belong to TF and P, but this may be hard, although we believe this is hard. There's a gap of doing it. So as an intermediate step, you can think about, okay, can we at least put those problems in this class and FP to the NP? And we will see that's not always possible. So let's at least sort of try to morally approach TF and P by putting them in a class that looks like that. Okay. So this is the thing. So there are many problems, and I'd like to talk about a few of them and see where they live, where they belong. So the first problem that I want to talk about is the linear ordering principle, L2P for short. So it's a problem that was defined by Korten and Pitassi in the paper. It was motivated and has a spirit. There are similar things in the similar spirit appeared in the logic literature, but let me tell you what the problem is. So we're given a relation, and then let me do it in formal first. what do we want to do? There are sort of two cases when it comes to this relation. If this relation represents a strict linear order, total ordering, you want to find the minimum associated with that relation. Now, of course, not every relation has to be a linear order. So what happens if it's not? If it is not a linear order relation, if the relation does not represent it, you have to report a violation. So this is sort of I'll make it a little bit more formal. This is sort of the problem, right? Given a purported relation, if it's a relation, actually a strict relation, find its minimum, otherwise report a violation. So now the fact that we have those two cases, that's what it makes it a total function. So unlike just the question, find the minimum, it's not a total function because the minimum may not exist. Here, because you have the other option of reporting a value, that's a total function. Regardless of what kind of, crazy relation you get, there is always a solution. You either have this or that. Questions, by the way, at any time.
Can you say briefly what FP is? Sorry.
FP is the functional part. So we talk about languages. It's P, it's polynomial time decidable. FP is functional. So these are the functions you can compute in polynomial time. So to solve TF and P, you typically are not looking for a decision, looking for some kind of a string, right? So this is polynomial time, but it's not a language, it's a function polynomial time. So actually, it's a good point. I'll keep going back and forth between this, but that's a good distinction to make. Questions? So the question that we ask, given the title of the slide, is the linear ordering principle in TF and P? Well, so there are all kinds of conjectures, all the things that we believe what will try to convince you that we're getting closer to the resolution of this question. So let me just make it a little bit more formal. So again, what's the formal side look? You typically are given this relation in some implicit form. So it's usually by a circuit on two n bits. So it's comparing n bit string with n bit strings. And if it is an order, you want the minimum. So you want an element which is smaller, according to this, older than every other element. Now, if it's not, you want to report a violation. Okay, so there are multiple ways to express a violation. Like, what's the violation of linear order? Well, there are multiple ways to put it, but one way to think about it is one of the two things happen. Either you violate transitivity or you have incomparable elements. So in most general case, these are the two things that can happen. You can think about other cases, but you kind of can reduce them to that. So it actually doesn't matter how you express that, but just for clarity, this is what it means to report violation. And
if it's given as a circuit, the second option is not really happening, right?
It could. The circuit could, you can get a circuit that does not represent a relation. What if you have a circuit that is constantly zero?
Oh, okay. It just tells you if it's not smaller than the other one. Like the circuit says, like the first half of the input is 1 if it's yes smaller, no if it's not.
So you can think about a C of x, y, right? X is n bits, y is n bits, right? So you can think about this is what a comparison means, right? The C of x, y is what the result of a comparison of x to y is.
Yeah,
Again,
no, I thought that it will say this is smaller than this, or it will say this is smaller than this, but you're saying no, that's not the way.
Then you flip them and suddenly that's.
No, I thought that CXY means 0, x is smaller than y, 1, y is smaller than x. But
Okay.
in that way,
If it's that way, then when you flip the inputs, you can say something inconsistent.
okay, and that will be the inconsistency.
yes, if it is sort of, that's the same. If it's inconsistent, you'll find this as a violation. You report. I mean, there could be other violation, but this is an example of violation, right? But again, that's the way this doesn't have to be, right? Or again, it could be that things are incomparable. Think about C of xy is 0 for every x and y, right? So, well, in this case, there may be a minimum or in some general sense, but that's a violation. Questions, concerns, complaints? So that's the problem. And now, based on this problem of the Lingonia principle, that's a search problem. They define a language class L2P. So what's L2P? It's the class of all languages. It's important that reduce in polynomial time to L2P. So I do have to say one thing. L2P is in some sense overload. This notation was used 30 years ago by Schoening to define a completely different class. There's a different class called L2P. There seems to be unrelated, but for the purpose of this talk and for now, I guess L2P means that, and not the other definition. So everything reducible to L2P. So now, once you define a new class, you want to explore. So they also started exploring it. So the first two things that you want to talk about and also gain an intuition is that it's one, Turing self-reducible, closed under Turing reductions, and two, it contains the class NP, so it's powerful enough. It's not trivial, it contains NP. So the first thing actually kind of follows from the definition. I'll mention that is you can define polynomial time reducible in multiple ways. In particular, we can define it to be polynomial time Turing reducible. So, and if you define it polynomial time Turing reducible, this sort of follows from the definition. Now, what's interesting is the second property. How do we do that? So I think that's an interesting thing to see because it actually sheds light on something that we need later. So let's see how we solve SAT, how we reduce SAT to LOP and how we solve SAT in this case, right? So I'm giving you a formula, what I'm going to do, and this may also help clarify the questions that we're here about, what an order looks like and what a circuit looks like. I'm going to define a circuit which compares or sort of purports to compare strings assignments. So here's what it's going to do. So giving to, this is what the notation, giving to assignments, A and B n-bit assignments, I'm going to look at the following. Okay, let me parse it for you. So this is just A and B as they are, but they are prepended. I'm prepending them with the value of phi on A, but the opposite of it. So this is phi of A, but opposite. So, and this is lexicographical order. So one way to think about it, I'm comparing A and B lexicographically, but before doing that, I'm putting all the satisfiable assignment before unsatisfiable. So the first bit says it's satisfiable or not satisfiable is already smaller, and then all things equal, you kind of actually looking at A and B as lexicographically strings. So this actually happens to be a total order sort of regardless, but what's interesting is the observation that the formula is satisfiable if and only the minimum of this order is a satisfying assignment. So this is, you can think about, that's the way it's written, it is a many-to-one reduction. Right? It's not just Turing reduction, it's a many-to-one reduction. So using those observations, using this idea and the fact that NP is an L2P, you can actually, you can define L2P, the definition is robust, you can define in multiple different ways. So you can talk about polynomial time reducible, you can talk about P to the NP reducible or many-to-one reducible. So pick any notion of reduction that you want. Because of those, it will give you the exact same class. So everything will lead you to the same L2P. Questions? So that's one total function, that a problem that we want to study. And now there is another one that some of you may know because some of you wrote papers about it, and this is the avoidance problem. So what's the range avoidance? For avoid, for short, it's a different problem, also related to circuits. We have a circuit that stretches n bits to n bits when m is greater than n. So m to n. And what the goal is to find a string outside of the range of that. So to find a string, which is an m-bit string, which does not have a pre-image. So this is where the name comes from, a string that a circuit avoids, hence the name. So a few comments about that. So it is, again, a total function. There is always a solution. Because of the stretch, there is always a string that avoids, in fact, the many strings. And this follows from what's called the inverse pigeonhole principle. And this is why this problem was studied before in the logic community and have a completely different name. They call it the dual weak pigeonhole principle. This is how they call it in the logic community because it is sort of something follows from that. So again, there are many solutions because of that. And now, what's the significance of that other than being an interesting and a natural problem? This is something that was observed by Korten, that this program captures explicit construction of your favorite pseudo-random and random objects. So if you ever wanted to get hard truth tables, PRG, cryptographic complexity PRG in instant Wigderson sense, Ramsey graphs, rigid matrices, etc., etc. So you can construct those things if you have a solution to avoid. Basically, you can reduce the construction of those other objects to avoid. And now, when I said if, it means that we kind of have to have an algorithm for that, an upper bound. So what's the upper bound? What are the known upper bounds? So the first thing that comes sort of from the observation is the fact that, going to use notation, is that it's in BPP. Actually, it's supposed to be FBPP, but functional BPP. Was to your question, because it's a functional problem, but I'm going to abuse it for now. So it's a BPP. Why? Because I can just pick a random string. If I pick a random string, I'm going to miss the range of serious probability at least I have. Well, it's good on one hand. On the other hand, it's actually bad because you actually don't know that what you got is a solution. So you don't know. And the probability half is pretty bad. I mean, you want something more than that, less than that. So if you actually want to certify, you can start playing this. You can start repeating and certifying with an empirical. This way you get FZPP to the NP, right? So you do it multiple times. You have a probability of success, but this time, every guess you use an NP oracle to certify that it actually has a pre-image. Well, you want it not to have a pre-image. So this was the state of affairs up until, I would say, a couple of years ago, until a breakthrough happened. We had a result of Chen and Ren, and then a result of Li. They've shown that you can do it in S2P. So I have to define what S2P is, but I'll tell you that S2P is a smaller class. I'll define it in a minute. If you don't know, it doesn't matter. I define it. So this was this big breakthrough. And again, we have to thank you for the progress and your co-authors. But the point is, one of the things that it allowed us to do, to see that many of those things, again, can be constructed in S2P, which again, up to that point for 20 or something years, I think it was, ZPP was the best thing. So it was the progress. And now, very, very recently after that, I mean, the timelines don't flip because there are the conferences, but very recently after that, it was sort of improved even further to another class called L2P. So I still have to define, but let me just again to actually say that, point out one inclusion diagram for you to understand. This actually is a progress, syntactic progress. So L2P, whatever it is, contained in S2P, contained in ZPP to the NP. Okay, so this is a progress. So now we are actually standing at the point where the smallest class is L2P. And again, I have to say, here it's functional, FZPP, F that, but because we're looking about, I want to talk about the languages, I'll keep it this way. Yes?
Does the problem become easier if you assume that M is larger?
If you assume what?
That M is larger than just...
Right, so a couple of things. One, so I mean, of course, the larger the stretch, the easier it is to solve because, I mean, even probabilistically, you can do it. For once, one result of Korten shows that if you're looking at polynomial stretch, if you're interested in P to the NP reduction, it doesn't matter. With respect to P to the NP reductions, a stretch of 1 bit or a stretch of n bits doesn't matter. So with respect to P to the NP reductions, I mean, you would say that the problem now, if you expect that, you know, at some point, you do it. So again, if the stretch is very, very big, you can just pick it in random, but then you don't know what happens, right? So the answer is yes, but at the point to your question, the answer is yes, but it seems that we don't know how to leverage that. More questions? So let's now try to connect the dots. We talked about linear order and we talked about that. So how do we connect the dots? So these are the two main properties that were shown. I mentioned some according, but I want to single them out is that One, you can reduce PRGs to avoid. So PRGs are many to one reducible to avoid. This was one result by Korten, and then the recent result that you can solve avoid in L2P, and I'll try to connect the dots. So these two results put together actually showcase even more power of L2P, show that this is actually more power than we thought. So if you remember, we saw that it can contain NP. But now put those together, we can actually show that you can do slightly more. You can contain MA. So MA is the class which is believed to be, well, it's syntactically larger. So this is NP with randomness, right? So it's not clear up front that you can go from NP to MA just like that. But as it turns out that with those two results, you can. So I think it's a very important thing to see. It's a very nice proof to see, and goes by steps. So step number one is to recall the framework of Nissan and Wigderson, hardness versus randomness, and to see that MA sort of, you can decouple in classes BPP or MA, you can decouple the randomness from non-determinism. So you can decouple that, and then you can replace the randomness, you can simulate, you can solve it using a PRG, a complexity stack PRG, right? So you can sort of decouple and do that. This is the framework of Nissan, and now
What does that mean exactly?
sorry.
What does that mean? You can decouple?
So NP, as you may know, it's non-determinism plus randomness, right? So
MA.
MA.
The verifier has some randomness.
Mhm. So what you could do is you could use if you have a PRG, if you have a pseudo-random generator, instead of using true randomness, you can run this algorithm on the randomness that's produced by PRG, appropriate PRG. So what will happen is that instead of usual MA is Merlin sends a witness to Arthur, and then Arthur uses randomness to verify it. So instead of doing that, Merlin can send witness, and now Arthur can use, instead of the true random thing, you can use a PRG to verify it. That would work for the exact in the framework of the same way that you can use a PRG to randomize BPP. It will work for the exact same reason. So all you need is if you have access to PRG, so you can use
Thinking of it as a black box,
yes,
this PRG?
yes, it's
It's a normal, it's a normal
Yes.
that will
Yes.
give you a polynomial number of pseudo-random strings, and you try all of them and take majority. Like using randomized people.
Okay.
yeah. So that's the same reason, right? I could have removed NP and write BPP is NP to the PRG. How would you do it? You would take, as Avi said, you take the random strings and run BPP on that. So here you can just decouple. So you kind of use non-determinism, and then you use the PRG on top of that.
Excellent.
Makes sense? So we can do that, and again, very fundamental result. Now, what happens next is then you start using those constructions. So first, you can reduce PRG to avoid. So you can replace PRG with avoid here, again, the same way. And finally, you can implement avoid in L2P, so which means that you can replace avoid with L2P. So far, so good. But now, what is this? If you read it, you read this inclusion, it's a language which is P to the NP reducible to L2P. That's exactly L2P, the way we define it. So this is, I think it's a very nice inclusion, but will come actually to our help later as well. So this shows that L2P doesn't only contain NP, it contains MP. Questions? And now, one thing that you can do in this chain of inclusions is you can here replace it with a PRG. You can replace the PRG with hard true stable, and this is again due to Nissan Wigderson framework. You can use the hard true stable to then create a PRG and then continue. But this is sort of shorter. So with that, once we have that, we can sort of something that I owe you. We talked about L2P, and we want to take some kind of a bucket list and compare what we have so far. So I actually want to compare two classes that I mentioned L2P and S2P, I'll have to define it, but let's see what's the relationship is. So we talked about L2P and we talked about its properties. I also mentioned briefly S2P, and I have to go back and do it. So S2P is a class originally was defined in terms of alternating, symmetric alternation, and that's a very nice definition, but instead to mimic L2P, I want to use a different path. So L2P was defined as a reduction by a complete problem. So you can define S2P using the same pattern, the same methodology for a different problem, of course. So here is a problem defined by Chakravarti and Roy called find IC. IC stands for irrefutable certificate. Hopefully you understand. So here is the problem. You're given a Boolean matrix implicitly as a big circuit. And now you have a promise. You have a promise that this matrix either has row of ones or column of zeros. So you have this promise. In general, the matrix can have neither. And of course, you cannot have both. You cannot have a column of rows and a row of zeros. You cannot have both, but it could be the case that you have neither. But here you have a promise. Your matrix either have a column of ones or a row of zeros. Now your goal is to decide which case holds. Is it the case of row or is it the case of... So this is find IC or irrefutable certificate. You can think about this row or this column as irrefutable certificate. So it turns out that you can define the class S2P as all the languages of polynomial time reducible to that, right? Sort of to mimic L2P. Again, there's a completely different definition using alternation, but that's iterative. So now hopefully you know what S2P is. So again, everything that reduces to that. So maybe also to help us, let's try to make it back at least and compare L2P with S2P. So what did we learn so far? So what do we know about S2P? Well, so it was defined from actually cryptographic motivation because it has a cryptographic meaning simultaneously by Canetti and then Russell and Sandram. And back then the goal was sort of there was this line of work trying to trying to put BPP in the polynomial hierarchy. So let's try to find the smallest class that containing BPP, right? The goal was to say, let's go to a smaller and smaller class. So let's find the sweet spot where BPP is located. And at that time, S2P was that kind of class.
And maybe it's good to say that both are closed under complement. S2P and L2P are closed under complement.
In fact, I want to say more than that. I mean, you're right, of course, but I want to say more than that. Not only they're closed under complement, they're closed under Turing reduction, which in particular includes complement. Yes, you're right. So in particular, what happens, you can show S2P that it contains MA. And as Avi pointed out, it's closed under complement. In fact, Turing self-reducible, closed under Turing self-reduction. Now, what else? So these properties were shown back in those papers. So now, what else do we know? And this is again, we have to think CHR and Lee is remember the fact that a void contains S2P. So what you can do, this maybe was the main motivation, you can actually inflate that. You can inflate it to the exponential. This is exponential S to E, the exponential version. You can show that because of that, S to E has exponential lower bounds. So this is the smallest. Now, I'm glad this was the breakthrough result. We had this class, which is the smallest class, which has S to E, the exponential version of S to P, that requires exponential lower bounds, as much as you can ask. So this is in terms of lower bounds. What happens in terms of upper bounds? Well, there are sort of two, how should I say, competing bounds because there seems to be incomparable. And one of them is due to psi, which show that it's ZPP to the NP. The other one is due to the same Chakravarti rule that defined this, is that P to the promise AM. So this is the promise version of the class AM, P to that ON. So this, I put it in the cap because we don't actually know how to compare them. So this is what we know about S to P, and let's try to contrast that with what we know with L to P and see what happens. So L to P was defined very, very recently. You can see almost a 20-30-year gap by Korten and Pitassi, as I've said. So it turns out that S2P is no longer the smallest class that contains BPP. L2 contains them, but you can also show that L2P is an S2P. You can show that this is a syntactic inclusion. You can show that this reduces to that by just looking at the complete problems. And it also shares other features. So it also contains L2MA, as we just saw, and L2P is also closed under Turing reductions. Has the same features. And now this was the case, and to add on top of that, a recent result by Korten and Pitassi shows the same thing, that you can have a void in L2P, which by the same virtue, if you can do that, by the same virtue implies that now L2E, the exponential version of L2P, is a class with no exponential, requires exponential circuit law bounds. So
exponential version of L2E means that a given circuit is of exponential size.
So
You want the linear ordering on what in the exponential version?
So something that reduces, okay, so this is actually one L2E. There are a few ways to define it. You have to define it properly. So one way to think about is think about a reduction, which is not polynomial time, exponential time reduction. So you're still reducing to L2P. I mean, you can take any circuit that you want, but now you can stretch it in exponential time. Okay, so this is one way to define it. By the way, to your point, there are two different definitions, and it's actually not clear that it gives you the same class. So it's a very good point. That I kind of swipe hand around, but I guess with you it's impossible to do it. But thank you for the question. So what happens is, yes, if you look at this definition, like the one that allows you to stretch that, that's what you get. More questions? Yes?
Oh, actually, do you have an easier proof of BPP in L2P without going through range avoidance?
A BPP, a proof of what, sorry?
BPP in L2P without going through range avoidance.
BPP and L2P without going through range avoidance. Yes. So, okay. Yes, because there is a. So I present the definition for L2P that I presented is the definition, which is, it's a sort of by a complete problem. Everything which reduces to LOP. So like here, everything uses to find. So the usual definition, kind of like historically, S2P wasn't defined like that. That was more like an observation. It was defined, if you know, through symmetric alternation. So what you could do, you could define L2P from a similar kind of symmetric alternations. You can, we can talk about this offline. You can do it as a sort of a game. We're playing two referees playing against two X and Y, yes and no, playing against a third person, but now it's more powerful. So one way to think about is that S2P, you can think about the bar Python graph, and L2P is like a single graph. So you can define it this way that doesn't involve L2P at all. And now, if you define it this way, then it's this is the same proof that shows that BPP is an S2P will show you that BPP is an L2P. And the same proof will also show that L2P is an S2P.
And this way of defining L2P, showing that it reduces to your definition with the linear ordering, that's not hard to see?
So you mean about the equivalence?
Yeah.
So I think it takes a in the paper of Korten and Pitassi, it takes a page and a half. I don't know. I mean, it's quite nice and very intuitive, and another the shorter way to do it, but it's. I think it's not hard to see. Yes, I mean, I'd be glad to talk about this offline if you want. But I mean, the reason I'm going this way because I think, and again, this is maybe a general problem. Many times you want to reason about the complexity class by identifying a certain complete problem. So you can think about LOP is complete for L2P, and finding irrefutable certificate is complete for S2P. More questions? So now upper bounds. Okay, so we have exponential lower bounds for L2E with the right definition. And now upper bounds, well, and it turns out the same. So as it turns out, well, we know that L2P is an S2P, but basically we don't have any upper bound on L2P, which wouldn't be an upper bound. Not to repeat myself. but without negations. Say it once more. All the best upper bounds or L2P are the best upper bounds for S2P. So if you kind of look at that list, it seems that well, they are different, but they're similar. They share a lot of characteristics, share a lot of similar features. In fact, all the similar features are there. So, we want to think about how do we maybe set them apart. So you start looking for properties which are something that will set them apart, something will distinguish them. And one thing you observe that S2P is a semantic class. It's defined with cumulative, but then L2P is a syntactic class. Is it well, it's true, but is it really a difference? Well, as we had discussion.
This is because of the promise.
Yes. Yes, this is semantic because of the promise. And but here, this was the question that Chris asked, what if you define it in different ways? So you can actually define, L2P as a semantic class as well, because if you use a second definition. So maybe they're equal, there are just two different definitions. So that's not really a deal breaker, but it is, semantic because of the promise. So I think this is what happened, my interpretation. One night, Korten and Pitassi were thinking about, how do we separate them apart? You check all the existing properties, they're all met. How do we separate them apart? And then they found one. And they found that S2P has what's called Karp-Lipton collapse. So if you don't know what it is, I'll explain it, but it's a sort of property. And then it seems that L2P doesn't have one. So this was one of the questions that they asked Korten and Pitassi, because they couldn't find, does L2P have Karp-Lipton collapse? Sort of, can we prove it? Again, I'll explain what it is, but can we prove it? So this was sort of one of many properties that you can think about, that this property actually separates them. Something S2P has and L2P lacks. So that's where we set up. Questions? So this is why it's a good time to talk about our result. So what do we show? So we prove new upper and lower bounds to L2P. Let me talk about them and explain. So the bounds are the following. So L2P contains P to the promise MA, and it's upper bounded by a different class, which I also have to define, but P to the promise SBP. So this is, again, new upper bound. And I'll show you a picture. You have to, if you don't know, again, SBP is, I'll show you, but to show you the picture, this is the new landscape. So MA in MA, so SBP is sandwiched between MA and AM. And then what happens is, so MA is contained in P to the promise MA. This is, also previously there was an error like this. There was an error. So we show that P to the promise MA is an L2P, and now this was something we knew before. L2P is S2P. Now, S2P previously had the upper bound that I mentioned, P to the promise MA, so this was known. So we show this thing in the middle. So L2P is contained in promise SBP, which is contained in promise MA, because this is true for regular classes, also for private classes. So our results basically put this to L2P in this place with those errors. This is the best known upper bound. This is the best known lower bound.
For SBP, everybody is happy with the difference between MA and AM.
I'll actually talk about it because
So you'll explain, or not everybody is.
No. I mean, that's my point is I wanted to talk about that because of what you said. Oh, but you're right. I mean, so people don't know. SBP is one of those classes that don't, in my opinion, deserve enough attention. So I want to talk about it. But as you said right before that was the case.
No, but yeah, just the difference between MA and AM.
Right. So to your point, Avi, SBP is the only known natural class between MA and AM. And to add an insult to injury, people have the trouble of differentiating AM and MA. And now we add more trouble to that. This was the point that you was trying to make. Indeed. And so it's there. And now from that point.
Maybe I'll say it right. MA is like NP. Approver sends a message to the verifier. And the verifier is allowed to just point. But there's only one message from this. In AM, they talk for a few times. Like the verifier talking points can ask questions of it. It's interactive. Some constant number of rounds. Yeah. So it's more powerful.
And now we add SBP to the picture, which complicates it even more, right? And the other thing is, from that point of view, it seems that S2P and PrSBP seem to be incomparable. So I don't know. At this point of time, we don't know which one is which. Sort of, they're both lie between PromIS-AM and L2P, both of them, but very comparable at this point of time. Questions? And now, by doing this, we actually solve an open problem of Chakravarti and Roy. There was an open problem that they formulated to show that PromIS-MA is contained in S2P. So they asked, does this class belong here, contained there? So it was open for 15 years. We solved it by placing it in L2P first, and this is already known. And another thing that follows from the upper bound is, remember, going to L2E. So L2E doesn't have exponential circuits. Oh, that's so for the appropriate version of L2E. So you can also use this upper bound and you can scale it. You can scale the P to E, translate it. So once you translate it, this P becomes E. When you translate it. So what you get is you get a new exponential lower bound for the class E to the PromIS-SBP. So again, this is taking this upper bound, scaling by factor of E, and then using the lower bound of Korten and Pitassi. And this is sort of as close as we get. We believe that it should be E to the NP here. This is what we believe, but again, there is a gap between what we can believe. So this gets us closer, one step closer to E to the NP. So this is the result, but I think it's important to talk about the content and sort of how it helps us. Questions about that? So one thing I do want to talk about, two things, and this is sort of what motivated us the first place to consider this particular constellation, and this was the open question, the separator between what was believed to be or considered conjecture to be the separating property of LP and S2P, and this is the Carr-Lipton collapse. Let me talk about that. So what is Carr-Lipton collapse? A fundamental results of complexity theory proved by Carr and Lipton is the following. What happens if NP has small circuits? So maybe some background, P versus NP, people try a whole bunch of things to separate them. And one approach was to observe that, well, P can computed by small circuits. So let's somehow show that NP cannot be computed by small circuits. If we do that, actually, well, I was going to talk about probably more soon. So not to steal anything, but if we do it, if we can show that NP doesn't have small circuits, we separate them. So of course we're not there, we're nowhere near there, but at least approach. So Carr-Lipton kind of tries to address it in a strong way by saying that this is probably unlikely. So the result says the following: if NP is NP-poly, if NP has small circuits, then the polynomial hierarchy collapses to the second level, sigma 2. That was the result. And now, since then, it has had some improvements in the sense of deepening the collapse. So the collapse went from sigma 2 to ZPP to the NP to S2P. So just to talk about this, so what happened originally you needed the alternating hierarchy to guess the circuit, but then in '96 came the learning algorithm of Bashuti that actually allowed you to learn. So instead of guessing the circuit, you can learn the circuit. This is how you get ZPP to the NP. And then subsequently, it was attributed in size paper attributed to Sengupta. It was shown that you can go all the way to S2P. So this is sort of what we know. At the same time, the paper of Chakravarti and Roy came that showed that you can go all the way to P to the PromIS-MA, which is in ZPP to the NP. So this was sort of the landscape of Carr-Lipton collapse. Sort of when we say a class has Carr-Lipton collapse means that if NP is NP-poly, then the hierarchy collapses to that particular class, right? So sigma 2 has it, S2P has it, P to the PprMA has it. So two open questions that motivated this. One, what's sort of the relative standing between these two? What's the relation between PprMA here and S2P here? And because sort of right now, this seems to be incomparable. And question number two, which is, can we extend the collapse to L2P? So it stops right now, it stops here. Can we go one more station? This was the open question by Korten and Pitassi. So I remind you, this was our result. So now if you take our result and you plug it in, you get the following set of inclusions. P to the PprMA is an L2P is an S2P is an ZPP to the NP and that. So this shows you two things. One, you can actually get Karp-Lipton collapse to L2P because we have Karp-Lipton loss for this class, and this is just a bigger class. In fact, if it here, it's in every other class which contains that. Two, it allows to line up all the known Karp-Lipton collapses. So every single class that we know that had Karp-Lipton collapse, we can line them up in this way.
You have a linear order.
Yes, exactly. A strict linear order, right? Well, maybe it's not strict, I don't know, maybe they're little, but at least a linear order. Now, there's an asterisk here I have to say. So the asterisk here is not because it's not true, it is true, but as it turns out, it's not that this is not all, there are nuances, there are other things you can do, but let me just say that our result remains true. We can still line up, have linear order of everything, line up everything. So this is result. Now, on my personal note, I mean, I have to say that I was thinking about this lining up Karp-Lipton since, for a long time, because to some extent, and well, hope Avi will understand, this is, I would think about this Karp-Lipton collapse in some sense as a, how should we say it? Maybe family matter. Maybe this will help you understand. So now, hopefully you can go and, report to Lipton that at least we solved, at least in our ancestry, we solved that.
You can put Karp as, near Lipton as like Boston.
This is also linear order, by the way.
It means that Karp was my postdoc.
Okay, that's a non-linear. Maybe we can put it. Maybe I can put it here next time I do that. Okay. So we can report to both. So questions about that? So again, I think we can line them up. And now, and the other thing that sort of I want to talk about is, okay, I mean, this whole hinges on this lower bound and P to the PprMA and L2P. So how do we actually, sorry?
Upper bound. It's a lower bound.
It's a lower bound for L2P.
Okay.
I mean, that I guess depends if you read English or Hebrew, right? Or which side you read. So you're right. So this all depends on this inclusion, right? So, okay, how do we do it? Well, I'm going to show you a movie that you've seen before. So remember, I've shown you this slide. This is the slide. This is the proof that MA is an L2P. That same proof that Korten and Pitassi had. Now, what happens here, and this is, sometimes people say it's a bug, I say it's a feature. So this is the first step is using a PRG, pseudo-random generator. Some people are concerned about that it doesn't only affect the class, it affects the promise class, but I think it's not a bug, it's a feature. So in the sense that you can replace the class with a promise class. So it was only, I mean, an observation. You if you observe this and you observe everything works, that everything works, that's exactly the same proof. But the point is, MA here, it's not enough to give the lower bound of MA here, it's not enough. It's not enough to tie it together to the existing Karp-Lipton collapse. This one is the existing Karp-Lipton collapse. Questions about that? And now the last thing I wanted to say, and this is to the discussion, I want to talk about the upper bound, but I want to start with talking about the class SBP, which I think doesn't deserve enough attention.
Doesn't deserve, but doesn't get.
Sorry, deserve but doesn't get. Okay, sorry. Deserve enough attention but doesn't get enough attention. Thank you. Okay. So people are focused on MA and AM, all this conversation, but sort of that. So this is actually a definition that, I mean, I want to put it, but I don't want to talk because this is a purely probabilistic definition. And just maybe one point, it's a very scary definition, but if you look at it, it resembles BPP so much. If I put here a quarter and a three quarters, I get BPP. What was the point, probabilistically speaking? To get BPP, you need two things. You need those probabilities to be different, and you need this number here to be bounded away from zero. So if you take away the second requirement, if you don't require the second probability bounded away to zero, you get SBP. SBP stands for small probabilistically small probability bound, small bound probability. Okay. So again, you can have as close to zero as you want. But again, I actually don't want to talk about that. I want to, again, think about complete problems because this, I think, brings more intuition to take. So
Still, just to digest it, you want the success probability to be, both success and rejection probabilities are very tiny.
yes.
Yeah, it's just the threshold is some exponential.
Yes, but again, I actually don't want people to think about it. I think there is a more natural way to think about it, using a complete problem. I mean, this is true. This is why I put it here. But again, to digest it or to think easier about it, there is a different way, again, using a complete problem. So meet the SSE, set size estimation problem. So that's a promise problem. We are given a circuit and a number. And what we want to do is we want to distinguish between scenarios. Case one, the number of satisfying assignment of the circuit is at least M. Case two, the number of satisfying assignments is at most M half. So this notation is the number of satisfying assignments. So it's a promise problem. We have to distinguish between the cases. So I think this is easier, to me at least, to wrap around than this probabilistic definition, but this is
But M can be true and you need to distinguish between 1 and 2.
in particular, yes. I mean, that can be any number that you want. Yes, in particular, it can be 2. This allows you to solve empty, for example. So this is the problem, again, given a circuit and a number, does it have at least M assignments satisfying or at most M half assignments? So if your circuit is, usual Boolean circuits, this is what's called SSE, set size estimation, but you can complicate the problem a little bit and use it for non-deterministic circuit. Same problem, you're given a non-deterministic circuit, a circuit where you have the guess input. So it's the same thing. You want to look at the satisfying assignments of this circuit's number of accepting paths and ask if it's at least M and most M half. So why am I telling you this? I already kind of hit it, but let me say it explicitly. So it's a promise problem, but you can do the same thing. You can show that you can define SBP as everything that reduces those. So this problem is promise SBP complete. So every SBP problem reduces to that. I mean, even languages, like it's also true for languages, but it's a problem. So every problem. So you can kind of, again, you can think about probabilities, as I said, but are very small, or you can think about, okay, SBP means I can distinguish between M and M half. Why am I telling you that? Because, well, this class was defined, this problem in this class was defined by this paper by Bowler et al. It turns out that for a long time, this problem, this class has a twin, sister, brother, cousin, whatever you want to call it. And it was already defined 20 years prior to that by paper by Goldwasser and Sipser, known as the Goldwasser-Sipser protocol. So what they've shown as the witnessed version, the non-deterministic version of this problem is in promise AM. This was used for it. But what it turns out that not only it's in promise AM, it's promise AM complete. So if you change the circuit, if you move from a normal usual circuit to a non-deterministic, you go from SBP to MA. And in particular, this shows this inclusion that we talked about, that SBP is an MA. You can also use it to show that. And in fact, SBP is the only known natural class that lies between MA and AM. Again, we already have problems with MA and AM. Now we have another problem. Yes.
Any way to capture MA using this kind of definitions?
One of my favorite open problems. No, I mean, if you know how to do it, please. I mean, this is. I was thinking about that for a while. I mean, I'm still thinking about it. If you have ideas, I mean, yeah, that's a very good question. Can we capture? Can we find something else? Well, it's like, just to think about it. If you want to go to MA, you have to relax the circuit, right? Going up, you can make it more general, like non-deterministic. Here you have to relax it. So I don't know how to do it.
Restrict, not relax.
Restrict, yes, I meant you have to restrict the circuit, right? So you have to restrict, so I don't know how to restrict it in a meaningful way. Yeah, that's a good point. So that's a very good question. Now, you can think about it. For me personally, when I saw that, was like, okay, this non-determinism, is it really that big of a deal? How big of a deal it is? So it turns out that this is a big of a deal because if you look at this, there are oracle separations all the way through in every possible way, in every possible shape. So that is probably non-trivial. So, I mean, I for a while thought that maybe we can somehow show that that's equal. So what you can actually show that, I don't know, this is an evidence against that or for that, is the following. If you can solve SAT using NP machine with sub-exponential number of accepting paths, then AM collapses to SBP. So again, I'm not talking about P equals NP, I'm talking about solving NP in polynomial time, or solving about, what's the usual way to solve SAT? You guess an assignment, but there are 2 to the end, there are exponentially many guesses. So if you can do it with less than that, so extreme case would be to think about class UP. UP is when you only have one guess. So that's an extreme case. So if you can, UP is still non-deterministic. It's still not polynomial time. But if you can solve, for example, NP with one guess or X sub exponentially many guesses, then AM collapses to SBP.
So this is an assumption that violates the exponential time.
Well, I guess, I mean, my take on that is, I don't know if it's an argument against that or for it, so.
Wait, Avi, is that true? Because he's just saying a number of accepting paths, right? There could be exponentially many paths.
Yes. So yeah, you said, so yes, that's it. That's my next question. We're talking about the number of accepting paths. We're not necessarily talking about how much time it takes to solve it.
Okay.
But so one of the things that I asked presented when presented, I actually asked people, okay, can you give me evidence? This was my next question. Actually, thank you, Rahul. Can you give me evidence for or against that assumption? So I don't know if it actually violates ATH or not, but think about. Okay, so. This is another thing. Now, what we show with regards to SBP is the following. We show that you can do approximate counting. Approximate counting is approximating the number of satisfying assignments. In this class, let me explain. It's polynomial time with an oracle to PprSBP, but your oracle queries can be done in parallel, non-adaptive.
What is approximate counting? Is it just this constant 2 replaced with arbitrary 1 plus epsilon?
So in general, so this is right to the problem. You give me a circuit and epsilon. I want to approximate the number of satisfying assignments up to 1 plus minus epsilon.
Oh, I see. So
that's approximate
binary search. It's this problem with.
Yes. So exactly the way you do it is you kind of use this oracle in the binary search method. That's why you can do it in parallel. Very true. Now, for a broader context, there are other problems, other classes that have similar features. I just want to flash it here. If you know it, good. If you don't, just to make sure it's complete. If you know, good. If you don't know, that doesn't matter. So it turns out you can kind of identify sort of 3 clusters of problems. So one is SBP. The next one is this problem called BPP pass. It's a different class. Which is, those of you who do quantum maybe know, it's BPP with post-selection. Again, if you've seen this before, good, but it actually turns out that BPP paths can be characterized using the same way, and in parallel queries, and then you can also talk about non-parallel queries. So there should be P to the promise BPP path. So you can sort of show that it's in the same color because it's equal. Questions? So how much time do I have? 5 minutes?
You have, yeah.
Okay. Let's try that. So I guess the last thing that I wanted to talk about was that is the upper bound. How do we show that L2P is in this class, or how do we place the linear order, solve the functional problem, and P to the F PprSBP? Okay, how do we do that? Like to give you ideas. So again, think about the order case, right? Whereas we have order because one observation is that if I give you an LOP which violates the order, you can solve it in P to the NP. You can find the violation in P to the NP, and P to the NP is a subclass of that. So I can assume that I'm in the case when there is no order violation. So I actually have a strict linear order. So definition, once you have a strict linear order, you can talk about order rank, right? You can talk about the rank of every element with respect to the order. So the rank is just the number of elements which are smaller than this element in the order. Now you can extend this notion to a set. In this case, it will be an average rank. So you can take, if you have a set, you sum up the ranks in the set and divide it by the size of the set. This is the average rank of a set. You can think of what's like an average from expectation. Now, what's the goal? The goal is to find the minimum, and something you can kind of see from the definition. Minimum means rank 0, right? We want an element that has rank 0. This is from the definition. So how are we going to do that? The idea is we're going to start with an arbitrary element and show that we can find an element with a smaller rank, constantly smaller rank, right? And we keep doing it certain number of times until we hit the minimum. That's the idea. So the question is how we're going to do it, how we're going to start from an element and increase its rank. So to that end, we define the set SA. So SA is for every alpha is the set of all the elements strictly or less than equal. Okay.
Just hit the key.
here
no,
it's
it's
fine.
back.
Okay, good. So they don't like alpha. Okay. So S alpha, it's that. So it's the set of all elements which are less than alpha. Now, one observation is the rank of the set will be exactly alpha divided by 2. It's the same intuition. Let's say you have a random variable which is uniform between 0 and m. What's the expectation? M half. Exactly for that reason. So now what are we going to do with that? And this is the following observation. So suppose I take any set T and I pick one bit and I restrict all the inputs which are xi 0 and all the inputs where xi is 1. So I'll partition my set where one bit is 0, one bit is 1. So what happens? You can show that if this happens, the minimum rank between those two sets is at most the rank of the original set. So it's like average. If I have the average of two numbers, weighted average of the numbers, the minimum will be at most the average. That's exactly what happens. So what's the idea? The idea is to try to find this element. So try to fix, starting with take an element and start fixing the variable, start fixing the coordinates n minus 1 and minus 2 in a way that yields the minimum rank. So every time, whichever you have to choose, if it's x1 or if you fix the bit to 0 or a bit to 1, you choose the one that gives you the smaller rank. You keep doing it until you're left with one element. And the rank of this element will be, this rank will be alpha over 2. So you show this way that you can start with alpha and get a beta, which has the rank of beta is at most rank of alpha over 2. And okay, this is a set of size 2 to the n, so the maximum rank is 2 to the n. So if you keep doing it n times, you're just going to get, or n plus 1 times, you're going to get to 0. So now, the only thing that you need to do that, you actually need to know which one to choose. So you need to know the rank of a set. How do you do that? So computing rank of a set is actually p to the sharp p hard. But as it turns out, you don't actually have to do it exactly. You can do it approximately if you count out the approximation. This is one of our results. We show that you can approximate the order rank of a set in this p to the PprSBP. You can approximate it. So that's how we do that. Questions? So summary, just on time, 1 more minute. So what do we show? we show an upper and a lower bound, and a way to do it, so the main meat isn't there, is the upper bound, is to show f to the p to the PprSBP procedure that can approximate count and approximate the order rank. Right? You can approximate the size of the set or the number of satisfying assignments, and they also approximate the order rank. Now, this allows us to get an algorithm that finds a minimum. So one thing I want you to note is that this can be done in parallel and adaptive, but finding the minimum, actually we lose it. Why we lose it? Because we have to choose 0 or 1. When you choose 0 or 1, the next query is adaptive based on that. We'll lose it. So that gives us the upper bound that we want. We get an upper bound on L2P and we get an upper bound on L2P because we can find that. So the question is, can we, yes?
I think like L2P contains P to NP, so I think you cannot do it.
Yes, that was my next question. So thank you for that. Let me formulate the question that you asked. So I mean, we know how to do it without the parallels. This is one of the upper bounds. The question is, can we do it in parallel? Can we do it with parallel or non-adaptive queries? Now, one reason we want to do that, as Hannon mentioned, is that in particular, that would place L2P in a class PP. We don't know that that's the case, but it will do it. Now, to the point is that would actually solve another open problem, which is we know that P to the NP is L2P. We don't know if P to the NP belongs to PP. That's an open problem. So doing that, if you can do it in parallel, well, put L2P in PP, but it'll also solve this open problem that Hannon was talking about. So can we do it? So the way that we do it, it seems that our approach is inherently sort of non-adaptive because you fix 0 and 1, 0 and 1. So I don't know how to do it. This is one question. Question number 2, what's the relationship between L2P and S2P? So are they equal? Again, there is a conjecture, there is a gap, what we can prove or what we believe. So no, but at least can we get the lower bound? So we have the upper bound of PrSBP. On that, can we extend it to S2P? So I remind you, the best thing here is PrMA for S2P. Can we do it for S2P? Can we put PrSBP, a class which is syntactically smaller, but not believed to be equal? And now, one recent result was that in the literature of total functions, there was a different upper bound on L2P. This is a potential line function. That's another TFNP class which I don't want to get into. So they gave a different upper bound, but it's not clear how their upper bound is related to our upper bound. I have no idea how even to start think about it. So if you know what it is and if you know how this may be related, talk to me on Tels, because this is something we have no idea how are they related. It's not even a conjecture.
Can you at least tell us what that stands for? UEOPL?
End of potential line. U is unique. End of potential line.
Okay.
It's a TF. It's a subclass of without the NP oracle. Of course, it's a total TFNP. It's a subclass of TMP, which again, sort of. I have to say that I know very. I mean, I read the definition. I know very little about this class, but people who know maybe, I'm glad. I'm always glad to talk about that. And finally, something that I didn't talk about, but just to put it there, there is this whole universe of oblivious classes which I didn't even touch, which you can also look at. See this whole framework in that. Spectrum in that lens, which I didn't even talk about. So if you know what it is, I'll be glad to talk about. But you don't know after that, but that's that. So that's all I have to say for today. Thank you for your attention.
Thank you. Any more comments or questions?
So there's this hypothesis or this question of any of NP with sub-exponentially many accepted paths, and you said would be interested in some assumption that would rule it out. Could you say more about that?
Yes. So not just rule out. I mean, either way, right? Sort of either way. So sort of you can think about the extreme case, which we have one of the people who defined this in the room, Adam Callender, defined UP and FUP. So what is UP is a non-deterministic, what you can solve with a Turing machine which has one accepting path. FUP, few as few, means that you can solve it in a Turing machine that has polynomially many accepting paths. Now we can sort of generalize it to talk about, okay, how many accepting paths am I allowing you? So here you can say, here what we're talking about is sub-exponential. The exact number is, the exact expression is 2 to the n to the 1 minus epsilon. That's the exact expression that we want. So just to repeat the conjecture or the premise is that if you can solve NP this way, then AM collapses to SBP. So this is the statement that was shown. Now, what I'm interested is to sort of how do we attach this to reality, right? So does it contradict anything? Does it support anything? This was my question. So I'm looking for any other statement or any other result or anything that you can offer that will say, okay, this is related to that problem or this contradicts that problem, sort of to say how realistic or non-realistic that assumption is. Because one thing that you can get out of that sort of in the contraposition is that there are local separation of SBP and AM. So if you kind of flip it back, you get that there is an oracle relative to which that doesn't exist. But some people told me that there are probably different ways to show it. There are probably a different way to construct an oracle where this happening without this collapse. So again, I don't know if this is an argument for the inclusion or against the inclusion. This is why I'm interested in anything positive or negative. Not just negative, positive or negative you can say about that. More questions?
All right, head to lunch.